So let's pick up where we left off. So what I'm going to do now is describe a new and general technique for simulating random oracles under quantum access that has a number of applications. So what I'm going to do is I'm going to run through a bunch of transformations of a random oracle and argue that each of the transformations is undetectable to an adversary. So for, in the random oracle model, we have a random function chosen uniformly at random, and the adversary makes quantum queries to this function. So one thing we can do is we can quantumify this random oracle. So rather than choosing a uniformly random oracle, what I'll actually do is create a uniform superposition over all random oracles and run the adversary with respect to the superposition of oracles. So it turns out that all the oracle queries and everything sort of commute with this quantumification, and so this does not affect the A's view at all. Another term for what we're doing is we're essentially purifying the random oracle. So if we think of the joint system of the adversary and the oracle, in the random oracle case on the left here, the joint system is actually not a pure state. It's a distribution over the state of the adversary for a given choice of oracle. But if we look at the joint system between the adversary and the random oracle, if we quantumify the random oracle, now the entire state becomes a pure state. And this sort of idea of quantumifying things isn't necessarily new. It's actually reminiscent of some old impossibilities for unconditional quantum protocols like oblivious transfer bit commitment. But this is a rather recent application of this idea. And so just to be clear with what I mean, so the adversary has their state that they're maintaining as they execute, which is something, and then the oracle is also going to have a quantum state. In the sort of typical random oracle model setting, we imagine the oracle state is just the truth table for this hash function. And now we're going to say, okay, it's actually a superposition over truth tables for the hash function. And when we apply a query is really a joint operation on the adversary's query, the X and Y, and the oracle state. And what it does is it just updates the Y value from the adversary's query to YX or H of X. All right. So we haven't done anything that interesting yet, just replaced a random value with a superposition over values, which is basically equivalent because you could measure the oracle state and it'll collapse back to a random value. But what we're going to do next is something interesting. So we're going to turn things on their head and look in the Fourier domain. So we're going to imagine we have this superposition over truth tables. And now what we're going to do is we're going to view the superposition over truth tables for the random oracle in the Fourier domain. So we're going to apply the quantum Fourier transform and look at what we get. And it turns out you can actually analyze the effect of a query in this sort of Fourier domain. So if we could imagine, between each query, we apply the Fourier transform, we get the Fourier domain random oracle, and then when we're going to process the next query, we apply the Fourier transform to go back to the computational basis, apply the oracle query, and then re-encode by applying the Fourier transform. But you can also work out exactly what happens to the random oracle in the Fourier domain, so you don't have to do this like decoding and apply the classical query operation. And what we see is two interesting things. So first, the initial state of the oracle is actually just a string of all zeros. All right, and this is because the initial state in the computational basis was the uniform superposition, and the uniform superposition is the Fourier transform of the all zero string. So by looking at it in the Fourier domain, our random oracle now becomes just, at the beginning of time, our random oracle just becomes all zeros. And we can also look at what the query operation looks like. And what's very interesting is that in the computational basis, the query operation wrote a value of h of x into the y register. In the Fourier basis, what actually happens is that the query writes the y register into a part of the oracle register. So concretely, there's multiple ways to think about what's going on. You can think about it as updating the Fourier register by XORing with the point function. But if you think about it just as a giant truth table, essentially what we're doing is x is an index into the truth table, and what we're doing is we're looking at the position of the random oracle at position x, and XORing y into the value at position x. I won't go through the full calculation of why this works. It's an exercise, but the intuition is basically that if you're applying a linear transformation in the computational basis, when you move to the Fourier basis, that linear transformation turns in, basically it's also a linear transformation, but it's the inverse transpose. Never mind the inverse. That's not so interesting. What's interesting is the transpose. And the transpose is really what makes us go from writing the values of the random oracle to the y register to flipping it, writing the y register to part of the random oracle. All right, so now we have this really nice view of what's going on in the Fourier domain once we've quantumified our random oracle. But we're not done. So what we're going to do is observe that, so our random oracle starts out empty, right? It's just, a zero string. Now, in the Fourier domain, it's just a zero string. Every time we make a query, we write a y value into a single position of the random oracle based on whatever the x was in the adversary's query. So if the adversary is making only q queries, a polynomial number of queries, what we see is that this h hat state of the oracle is a superposition over truth tables that are non-zero at no more than q points. Maybe it's non-zero at fewer than q points, because you could have written 0 into the oracle or something like that. But certainly it's no more than q. We start out with completely empty, and each step we write at most 1 point. So we have at most q points that are non-zero. And so what this means is we can actually compress now the oracle state into something small, something that's only of size at most q. And concretely, what we'll do to do the compression is we'll just remember the x's where h hat is non-zero, and remember the corresponding non-zero y values. And so this gives us a compression of this random oracle. And we can also, and this compression is, a bijection. Given the compressed oracle, we can go back to the full oracle just by decompressing, filling in all of the unspecified positions with 0. So we can actually work out now what the queries look like on this compressed oracle. So the compression of the all zero string is just empty. At no position is it non-zero. So the initial oracle state is just completely empty. And then what do we do? So to update the d hat, so I'm calling d hat the compressed the compressed oracle here. So when we make a query, what happens is if so if there's no entry in our database for X, that means in the uncompressed version, the database had 0 for X. So what we're going to do is we're just going to insert X comma 0 into our database. So we haven't actually processed the query yet. We've just sort of expanded out we've uncompressed the part just for input X. And then what we do is, right, what does the query do on the uncompressed database? Well, it XORs Y into whatever the contents were at position X. So now that we've uncompressed the position X, we can just XOR Y into whatever the contents are at position X. If XY was already in the database, then if there was an XY prime already in the database, there's no expansion. We just directly XOR Y into the Y prime register. If there was no XY prime in the database, we add an XY prime into the database by setting Y prime to be 0. And then finally, we have to sort of maintain the invariant that we're a compressed database. And a compressed database means we have no XY pairs where Y is 0. So if the result of doing steps 1 and 2 means that the entry in the database actually had the Y coordinate be 0, we remove it from the database. And this maintains the invariant that D hat is a collection of XY pairs where Y is non-zero. All right. All we've done so far is a handful of simple transformations, and these are completely oblivious, or the adversary is completely oblivious to these transformations. You can just think of it as sort of locally encoding the Oracle's database in a different way, and then working out what the Oracle query was, what the Oracle query's effect was directly on the encoded database, rather than sort of decoding the database, applying the query and then re-encoding it. So one final step that we do is we revert back to the primal domain. So all the Y entries in our database sort of roughly corresponded to, basically they corresponded to the Y entries in this Fourier transformed database. So why don't we go back and un-Fourier transform, go back, set the Y's to be back in the primal domain by applying the Fourier transform to all the Y entries. And what we get is something very interesting. So what we get is a database of input-output pairs. And what's interesting is that it's roughly analogous to classical on-the-fly simulation, right? Every time we make a query, if they're on a superposition query now, but still a query, and the query input register contained X, what happens is we look up X in the database. If X is there, we do some operation based on the Y contents, and if X wasn't there, we sort of insert a new XY pair. So the inputs in this database basically are the points that the adversary cares about. They're really corresponding to the points that the adversary queried. And the outputs, there are caveats that we'll discuss as we go, but the outputs roughly correspond to the corresponding outputs of the Oracle as seen by the adversary, right? Because we Fourier transformed the outputs, did some compression, but then we Fourier transformed them back. And so these Y's really roughly correspond to the actual outputs. So what we see is that we have something that, at least, vaguely resembles the classical on-the-fly simulation, but it works for quantum queries. The quantum algorithm is none the wiser to our simulation. Let me just pause here before I go on to see if there are any questions?
I think we're good for now.
Okay. So what do compressed oracles give us? Well, they tell us which points the adversary cares about, because they're there in the database. We know the corresponding outputs roughly anyway, because they're there in the database. And it turns out that we can even adaptively program the outputs. Though this one actually requires some work. And the reason that this requires work is that, and actually sort of all of these require some work, because everything's in superposition, we have to be careful still when we sort of access the entries in our compressed database. We have to be careful that accessing them and doing stuff with them isn't completely messing up the adversary. And this is so we're not done. This doesn't immediately give us any application, but it at least it provides an intuition for why we should be able to now look at what inputs the adversary cares about, know the corresponding outputs, and maybe program, because we're really accomplishing something that looks like the classical on-the-fly simulation, which allowed for all of these. So stepping back, I think it's useful to just try to understand what on earth happened. Why were we able to get something that looked like on-the-fly simulation, despite all of these difficulties that we had talked about before that motivated this notion of a committed programming reduction? Well, it actually all has to do with this thing that I call the observer effect. I mean, the observer effect has been described by physicists for a long time, but I'm sort of applying it to the problems that we're thinking about. And the observer effect roughly says that learning anything about a quantum system will disturb it. And this is sort of the origin of no cloning or uncertainty principle and all of that. And this and the motivation for the committed programming reductions is that a true random oracle, answers all of its queries obliviously. And what this means is that by answering obliviously, it's not disturbing the adversary state, other than of course by writing its answer into the adversary's registers, but otherwise doesn't disturb the adversary state. There's no measurements or anything like that. And so the intuition that we had was that because H answers obliviously, our reduction must answer obliviously too. Otherwise, the observer effect will mean that we're disturbing the adversary state, and the adversary could detect that and refuse to cooperate. So the observer effect was our motivation for committed programming reductions. But basically what we've done is we've turned things on their head, and we've noticed that the fact is that A is learning about the random oracle by making queries, right? That's the whole point of making queries, is to learn something about the random oracle and its input-output behavior. And so if we think of H itself as a quantum system, the observer effect means that H gets disturbed. So as A is learning anything from H must necessarily be getting disturbed if we think of H as a quantum system. And that's the very first step was to replace H with a superposition over all H. And that's why, and basically now we know that as A learns something, H gets disturbed. And basically what the compressed oracle does is it decodes this disturbance. It actually sort of figures out what the disturbance is sort of automatically, and records it in this compressed oracle database. So this is sort of an idea of like why this seemed to work. Now the point I want to make though is that we're not done yet. So the compressed oracle decoded the disturbance that was inherent to A learning about the queries, but in a reduction, maybe we're going to end up further disturbing the adversary by doing things like reprogramming the oracle. And so we still have to be careful. We have to tread carefully. We're not necessarily done, but at least we got something. Right. So there are some caveats to this. So remember that before we did the final Fourier transform back to the primal domain, so after the initial compression, while we're still in the Fourier domain, our database only consisted of entries where the y value was non-zero. We basically poked a hole in the in the database entry for x. If x is in the database, we sort of removed the y equals 0 Fourier component. And what this means is once we move back to the primal domain, these y values aren't exactly the query outputs. We really did modify them when we moved to the Fourier domain and compressed. So they're not exactly the query outputs. They're rough analog of the query outputs, but not perfect. And also, as I've been saying, if I were to actually examine the XY values in the compressed database, by the observer effect, examining those values will perturb the state, and this could be detectable to the adversary. So we still have to tread very carefully with this compressed oracle technique. But it turns out that by being very careful, we can actually get a number of applications. So you can show the indifferentiability of Merkle-Damgard. We gave some tight bounds for finding multi-collisions. This technique was used to prove the Luby-Rakoff construction remains secure under quantum superposition queries just by increasing the number of rounds. It was used to construct zero null succinct non-interactive arguments and a handful of other things. And actually, in a concurrent work with the Fiat-Shamir result that I mentioned earlier, we actually showed how to prove Fiat-Shamir using this technique, though our proof is much more complicated and also incurs a worse loss in the reduction. And in the remaining time that we have, after I give a brief summary, I'll actually show how we can view the Fiat-Shamir proof from earlier today. We can actually view it as sort of an instance of this compressed oracle, and hopefully by doing so give some intuition for where the magic came from. So
maybe we can take some questions before we move on.
Yeah, I was just going to give a brief summary and then pause for questions.
Okay.
So summary is, basically we have numerous techniques for proving QROM security now, either through committed programming reductions or adaptive reprogramming through various means, or just tweaking the scheme in various ways. And the result is that many schemes of interest now have a quantum random oracle proof. But there are some lingering issues. A major one is the tightness of reductions. The reductions in the quantum random oracle model tend to be worse. And the reason we care about tightness of reductions because it helps us set security parameters and stuff in practice. Indifferentiability has been not that well explored. So for example, can we prove the indifferentiability of the sponge construction is sort of another way of building a hash function, or can we build ideal ciphers from random oracles? I think another big open question is, can we get a lifting theorem, a general lifting theorem for indistinguishability type games? We're still going to be limited to the constant query setting probably, but can we get indistinguishability? The issue with indistinguishability is that our current lifting theorems incur a polynomial loss, and that polynomial loss kind of destroys any indistinguishability guarantees. And then there's just some various missing pieces. We haven't gone through all of the literature yet and updated all of the proofs to the quantum random oracle model. So there's still various missing pieces, but these are sort of, in my mind, some of the big open questions. So now I'll pause for any questions that have come up so far.
So I guess there are a few questions regarding the compressed oracle technique. So for step 1, the purification, there is a question that asks, does the fact that we are working with the purified states add extra steps?
I guess I don't quite understand the question. So, I mean, all we've done is we've interpreted the evaluation of the oracle as a sort of a joint unitary on the query and oracle state. Yeah, maybe actually implementing this would require sort of rewiring your unitary circuit, but it's nonetheless something routine that you can do. And once we're imagining the query as a joint operation on the adversary's query and the oracle state, then replacing a random oracle with a superposition doesn't really change anything in terms of extra steps or anything like that. I don't know if that answered the question.
Okay, and then for step 3, there's a question asking what would be the intuitive argument that the compression are reversible, or in other words, the compression is lossless.
Good. So intuitively, it's just because we have this giant list. Thinking of h hat as just a giant list of values, we know it's 0 almost everywhere, and there's at most q positions. So all we're going to do is remember exactly the q positions that are non-zero, and we need to be careful. We want to make sure we don't remember any position that is 0, because then the compression won't be bijection. So remember exactly the positions that were non-zero, and we remember the non-zero values for those positions. This is just it's just a classical compression of strings with basically low Hamming weight. And we're just applying this compression in superposition over the entire oracle state. And so it's by being a classical bijection that we're applying in superposition, it's still reversible.
Okay, and related to that, in step 3.3, in the later slide, why is it necessary to remove x0 from the database?
Right. So this is it's a very subtle point. So the reason is, imagine that what we did. So the adversary makes a query. We put an entry in our database. And now let's say the adversary were to uncompute that query. Well, if the adversary uncomputes their query, if we sort of go back to the step 0, the original random oracle, basically the adversary state becomes completely unentangled, independent of the random oracle if they uncompute the query value. And so what that should mean is that when we move to a compressed oracle, the database should be empty. It should look just like it did when it started, because in the original uncompressed setting, everything looked just like it started. And maybe a little more concretely, if you don't remove this value here, what it means is that you'll have some entries in your database that are 0. And when you try to uncompress, this uncompression will now no longer be a bijection. Right? Because basically, if you have an entry that's 0, or you just didn't have an entry at all, those will decompress to the same uncompressed database, meaning that your operation is no longer reversible. And so really the only way that we have to ensure that everything works is to make sure we always maintain this invariant that our compressed databases have when we're in the Fourier domain anyway, that our compressed databases have the property that the y value is non-zero. Otherwise, our compression won't be a bijection, and therefore we can't implement this in a unitary. And worse, it will mean that the state of the oracle could actually end up even if the adversary uncomputed everything and returned to the original state, there might be something left in the random oracle, and then the adversary could potentially distinguish. So hopefully that made sense.
Okay, and I guess lastly we have a quite general question asking what happens if the adversary queries an equal superposition of X. How will the compressed oracle handle this kind of query?
So it's just automatic. So what would happen? So concretely, what would happen if you did a uniform superposition over X? What the database would have at the end of that, and at the end of the query, is the same uniform superposition of X. So not like an independent uniform superposition, but like if we did a quantum copy operation from the adversary's X into the oracle. So you'd have like superposition of X comma X. And then for the Y registers, it would actually also, it would almost be a uniform superposition, not quite, because there are sort of these subtleties with the fact that we did the compression. But basically you'd have something close to the uniform superposition over Y's in the Oracle database as well. And then those would get quantum copied into the adversary's response registers for the query.
Okay, there's another question asking, would there be any analog of this technique which could help fix our earlier issues with reductions that guess an index? For example, in Fourier reduction, we guess which query to measure.
Yes. So that's actually, we will see this in the second half of this hour, where basically it turns out that you can kind of sort of do this sort of per query guessing, where you guess a random query and do something on that query. There are issues getting everything to work, and the issues sort of end up resulting in the algorithm for Fiat-Shamir we saw in the first hour, where we had to do this tweak with the reprogramming. But yes, as long as you're very careful, it does allow you to do a sort of per query kind of guessing of a random query or something like that.
Okay, I guess that's all for now.
Okay. Okay, so right, in the last 25 minutes, I guess, I wanted to just, this Fiat-Shamir result, I personally find very mysterious. It's sort of amazing that it works, and I just wanted to give sort of my own intuition for, or maybe a way that you could try to derive this algorithm from sort of intuitive principles. So to do so, what I'm going to do is take a slightly different view of what quantum mechanics is. So I believe in the sort of the boot camp on Sunday, quantum mechanics was compared to sort of general stochastic processes, talking about matrices and vectors and norms and stuff like that. And I'm going to kind of do the same thing, but with a slightly different perspective. which is a path, which uses this notion of paths. So for a classical stochastic process, we imagine starting, our system starts in some state, and then there's some, probabilistic procedure that, updates our state. Maybe it sends the state with probability half up here, sends state with probability 0.1 down here and 0.4 down here. And then we can imagine, composing stochastic processes together. So we have another probabilistic procedure that updates the state again and another state again. And then suppose at the very end, we try to observe the state of our system. So in the classical stochastic setting, you can actually, explain what the probability here is by asking, by sort of reasoning about the paths that our system took through the system. Right, so a path is just, connecting it's just a line through the various states at different points in time. And we'll say that for a particular path, the weight of the path is just the product of probabilities along the path. And I'll denote this by probability P. So it's really just the probability that, if you're thinking this as a particle, that the particle actually took the given path through all points in time. The probability of seeing y then is just the sum over all paths from the starting state to whatever value. It's the sum over all paths that connect these two nodes of the weight of that path. Okay, so nothing fancy here. When we move to quantum, basically what we do is we replace the stochastic probabilistic process with a unitary. And so these weights now are no longer probabilities, but complex amplitudes. But nonetheless, we can define the weight of a path as the probability, as the product of the weights along the path, except now the probability of a particular y value is not the sum of the weights of the various paths, but the sum of the weights and then squared. All right, so what's the main difference then between quantum and classical? Well, I mean, I guess you probably already covered this, but the point is in that when we look at the quantum setting, these paths can interfere constructively or destructively even, amplifying probabilities or eliminating them. In particular, if you have paths with like one path has a positive weight and one path has a negative weight, that could actually cancel out and result in a zero probability, even though there's like non-zero paths that go there, and you can also amplify the probability. Maybe this isn't so important, but basically this path view, I think, gives a nice intuitive explanation of a lot of the quantum effects that we see. So one is this sort of observation effect or measurement principle, whatever you want to call it. So in the classical setting, imagine we wait to the end to measure y, but also at some point in time we peeked in at the system and looked at what state the system was in. Well, the probability of seeing x and seeing y is just the sum of the weights on all paths from S that go through x and terminate at y. And if you do a calculation and you suppose you looked at x, but then you forgot it, and you actually just want to compute what's the probability of observing y. Well, that's just the sum over all x of viewing x and y, and just by linearity, you end up with probability of y. So, basically what we see is that looking at x for a classical stochastic process, looking at some intermediate state of the system does not affect the final outcome. On the other hand, when we move to quantum, we see that the probability of x and y is still the sum over all paths from S to x to y, but now we square the final sum. But the square kind of breaks things, and if we sum over the probability of x and y, we actually don't end up with the probability of y. And what this means is that observing X as an intermediate state of the system actually changed the Y, changed the probability distribution of Y. Okay, so this is just I think a nice path view of what happens in quantum computing, and you can use it to explain no cloning or any of those things as well. But we won't do that. Right. So, but this is sort of the origin of the observer effect, that learning anything about a quantum system disturbs it. So now what we can do is give a path view of sort of a quantum query algorithm. So for every query, we can ask, what's the state of the system at this time? And I'm going to sort of ignore the state of the adversary just for simplicity, and just think about the state of the actual query that the adversary is sending. So every possible state is indexed by a pair XY, where XY corresponds to the contents of the query registers that the adversary is sending. And now I can and basically what happens between, so every line here, every point in time is a particular query. And what happens between the queries is I first apply the query operation that XORs H of X into the Y value. So it sort of permutes these states by XORing H into the Y values. And then it applies whatever the adversary's unitary is to sort of further direct the paths around. So I'm going to think, though, of the sort of the snapshots in time of our query algorithm as the various queries the adversary makes. So with this path view, we can actually ask what does a compressed oracle do? And it turns out that if we look at the compressed oracle in the Fourier domain, what it's actually, or let's even think of the uncompressed oracle, but in the Fourier domain. So after we did this Fourier transform, remember what happened was that every time you made a query, you XORed the Y registers into the corresponding location of the oracle. And another way to view what that Fourier oracle is containing is actually the parity of the current path. And so what is the parity of the current path? It's at every, so the parity is sort of a function of X. And at X, it's sort of, you look at the paths that were taken, you look at all of the Y values for that particular X that were on that path. So the particular path goes through some X1, Y1, X2, Y2, X3, Y3, as you're doing all these queries. And for a particular path, you look at for any particular X value, you look at all of the XY pairs along that path. There might be none, but if there are some, you XOR all the corresponding Y values together, and that gives you what I'm calling the parity of that path at query X. So one way of thinking about the compressed oracle then is that it's really recording some information about the current path. You can't record all of the information. So all of the information would be the complete list of XY pairs, which would correspond to basically measuring, the query at every point. So we can't record that. That would actually, the adversary would be able to tell. But when we look at the oracle in the Fourier domain, essentially what we see that's happening is we're recording the parity of the adversary's path. So many paths will have the same parity, but paths with different parity will sort of result in different functions in the Fourier domain. Let me actually just pause here to see if there are any questions about any of this path any of this past stuff.
I think we're good for now.
Okay. So a couple of things that you can show, and these are informal, but they're good for gaining an intuition. So if the parity of a path is 0 at x, this could either be because there's no query on that path corresponding to x, or it could be that you made a query on the path, but then you later uncomputed your value. Regardless, if the parity of the path is 0, the path actually has no knowledge of h of x. And so in order to actually have any knowledge of h of x, you must have paths that are non-zero. And as a corollary of this, if we're thinking about Fiat-Shamir, any successful path, so if we sort of condition on the adversary succeeding, this means that the challenge that they replied with actually was the random oracle evaluated on their commitment. It must mean that by the time they produce their final proof, and we condition on them succeeding, basically all of the paths that we have must have the parity of that path be non-zero at whatever comm the adversary produced. So what we're going to do is we're going to imagine now we've sort of run the adversary to completion. We've tested whether they succeed, and we're going to condition on them succeeding. What we see is that the only paths that can lead to such a success must have the parity of the path at the particular commitment that they produce be non-zero. And in particular, this must mean that they must have queried commitment. That path, all of the paths at the end there that led to the successful adversary, those paths must have at some point gone through a query at comm. So what we're going to use then is something that I'll call an observation lemma, which says that if you observe x at some prior point in time, we know that you're actually disturbing the state, and you might reduce or you might change the outcome of a probability y, but you can't change it by too much. And in particular, if x was only had one of t possible outcomes, the probability of any y drops by at most t. So if t equals 1, this is basically gentle measurement, saying that, well, if I observed x and x was already classical, I didn't change anything. But more generally, if t is something like polynomial, observing x only reduces the probability of y by a polynomial factor. And I won't prove this, but it's a simple consequence of Cauchy-Schwarz or Jensen's inequality, and looking at just the equations for what y is versus y conditioned on x. And it turns out we can generalize this to paths. So if I partition my paths, and then I somehow observe which partition I'm in. So if I partition all my paths through the entire computation, and I make sure to only have t partitions, and I somehow manage to observe which of the various partitions I'm in, a similar consequence of Cauchy-Schwarz is that this observation will not reduce any output by too much. So I can basically observe which path I'm on, or not which path because there's too many paths, but I can observe which partition my path came from without destroying my state too much. So the name of the game then is to come up with partitions of the paths that we can measure but make sure that our partitions aren't too big. And so here's one example. This isn't going to work, but it nonetheless is a warm up. So what if my partition is as follows? So I'm going to call pi all of the successful paths. So these are the ones that ultimately led to the adversary succeeding, where the path had a parity of 0 on the commitment, the final commitment that the adversary produced, just before query I. So right when the adversary makes query I, at that moment in time, before I've actually applied the query, the parity of the path was 0 on the commitment. But then after query I, the parity of the path on the commitment of the adversary remained non-zero for all remaining points in time. So this is a partition. Why? Well, we know that the parity starts out as just uniformly 0 for all values. And we know at the very end, the parity of the path on commitment has to be non-zero. And this means there must exist sort of one point where the parity of the path became non-zero, went from 0 to non-zero and became non-zero until the end. And that point will be I. So we're partitioning all possible paths based on this. And we can actually sample sort of an execution of the program that follows the paths in the partition. Basically, what we do is when we guess an ith query, and when we make the ith query, we observe the commitment just by measuring the query, and then we observe whether the parity of the path was 0 at that point. And we can do this by looking at the compressed oracle database at the given time. If the parity of the path on the commitment is non-zero, we abort. And then otherwise we just continue. And for every remaining query, we just make sure to observe whether or not the parity of the path on commitment is 0 or not. And if it is, if we ever go back to 0 again, we abort. So what this has the effect of doing is selecting all of the paths where the parity of the path at and then finally at the end, if the adversary doesn't output the commitment that we measured, we just abort. And what this does is it has the property of selecting just the paths that are 0 immediately before query I. That's what this abort does, is it rejects all paths that were non-zero immediately before query I. We prune out all paths that ever become 0 again. And if the adversary doesn't output com, then we also prune that path. So we make sure that we outputted the right com. So this algorithm actually samples from the PI partition. Now, so we lose a factor of Q due to the observation lemma from Cauchy-Schwarz, and we lose another factor of Q because we have to guess which I we're in, and we might end up being wrong. If we didn't guess the right I, we'll end up aborting here at the end. But if we guessed the correct I, then we sample from the correct PI partition. So the reason that this doesn't work is it doesn't actually let us program into the random oracle. We now know what com we have, so we were able to extract com and maybe send that to the verifier, but we don't know how to embed the challenge into H. What we can try to do is reprogram the random oracle just by setting the contents of the compressed database. We can set the contents to be the challenge we got from the oracle. And the good news is that because the parity of the path was 0 at this point, the adversary had no knowledge of what H of com was, and so we can set it to be whatever we want, and the adversary can't detect. The problem, though, is that the parity of the path was sort of stored in the Fourier domain, and when we replace the contents with CH, the Fourier domain gets destroyed. It becomes, the Fourier domain just becomes a uniform superposition over everything. And so we no longer have access to the parity of the current path at the commitment. And this means if we try to do this adaptive programming, we break things because the because we can no longer do this test here where we observe if the parity of the path is 0 at all points after j. And what this means is we're no longer actually sampling from the PIs, and we have no more guarantees that anything will work, because we're not sampling. If we're not sampling from our partition, we don't know what happens. So the solution, okay, well, let's give an alternative partition. This one also doesn't work. We could have equivalently defined PI as the successful paths where the parity of the path was 0 for all queries before I. So it's right. So we know that the parity of the path at com went from 0 to non-zero. Our previous partition sort of partitioned by the last transition from 0 to non-zero. We could have equivalently partitioned based on the first transition from 0 to non-zero. So PI is basically the set of paths where the first transition from 0 to non-zero happened at query I. So it's 0 for all queries before I, and then it's non-zero immediately after I, but we won't say anything about what happens for subsequent queries. Maybe it goes non-zero, maybe it goes 0 again, non-zero, non-zero, 0, whatever, many times, but the first time it transitions is at query I. The problem with this partition is we actually don't know how to simulate it, because in order to sample from this partition, we actually need to know what com is. But we don't know what com is until we've observed the ith query. But this means we can't do the check that makes sure that the path is only 0 for all queries before I. Because at the queries before I, we don't know what com is yet. We only learned what com is at query I. So the sort of takeaway is that we need a partition that doesn't check the parity of the path once we've programmed it. So once we've programmed it, we've lost all the parity information because it's in the Fourier domain, so we can't check. And on the other hand, we need a partition that doesn't check the parity before we observed com. Because before we've observed com, we haven't yet measured anything, so we don't know what com is. And so what we're actually going to do is define another partition. It's not going to be exactly a partition. So what we're going to do is define QI as a successful paths where the parity of the path is com. The parity of the path is 0 immediately before query I and non-zero immediately after I, but otherwise we don't say anything. So it could be going crazy. It could be 0, non-zero, 0, non-zero, 0, non-zero, and we're going to collect it in Q sub I as long as it made a transition at query I. Now the problem is that this isn't a partition, because any path that goes from 0 to non-zero multiple times will be counted in multiple different collections. But it turns out that we can sort of compensate for this by looking at the successful paths that were by basically flipping things, looking at the successful paths that were non-zero just before query I and 0 just after query I. And maybe because I'm out of time, I won't explain it more, but you can sort of justify that any overcounting that happens in this partition will be exactly the number of counts in this partition. And so in some sense, even though these don't correspond to an actual partition of all paths, the fact that we just exactly compensated for the overcounts means it sort of works as a partition. So the final algorithm basically either selects from QI or selects from one of the RI, the choice being random. And essentially what the Don et al. Fiat-Shamir algorithm does, it will require some staring at it to sort of figure out, to do the mapping. But essentially this is what they do. This is not how they explain it all, but this is what they do. So if you reprogram the random oracle at query I, you're sort of doing a QI partition. And if you reprogram the random oracle at query I+1, you're doing an RI partition. And so you can sort of view their algorithm as sort of doing this partition kind of thing. And this is why they needed to do this compensation where they selected randomly to reprogram at query I or I+1. It was sort of to exactly compensate for the overcounts in the paths. And I'll just mention that in a concurrent work, we gave an analysis sort of, doing this path thing. We didn't use these partitions, we used something else that was crazy and resulted in much worse reduction. But after the fact, we sort of realized that you can view the Don et al. Algorithm in sort of this way. And with that, I will stop. Hopefully this, made some sense and maybe lifted the veil off some of the mystery of this Fiat-Shamir result. And I'll take any questions now.
Yeah, we don't have any questions, but I guess we can go back to a question that was asked on Slack earlier,
Okay.
which was related to the failed Fiat-Shamir proof. So the simulator in the earlier case for the failed Fiat-Shamir proof, was it like we were not able to show the correctness of the simulator, or there was like a very specific attack on the simulator?
Yeah, so I don't actually know if there was an explicit attack on the simulator. Right, the simulator, the simulator that basically, it would correspond to just doing these QI partitions where you just you reprogram immediately on the ith query. I'm not aware of an explicit attack. I sort of suspect that you could come up with one if you tried hard enough. But really the reason for doing the extra stuff was to make the math work out. So the short answer is I don't know, but I suspect there is an attack.
Okay, thanks. I think we are done with the questions on Slack.
I think I have a question. So,
all right.
Going to the takeaway page. No, like before the take. Yeah.
Yeah.
No. No, like after that.
Later.
The takeaway page.
I forget which the takeaway page was. Was this in the first
later?
half of the hour? Later.
No, second half.
Okay. This one. Okay.
Right, this one. Yeah. So doesn't the fact that you observed com tells you like the parity of com becomes non-zero after this query?
More or less. So if the Y register contents were in a uniform superposition, when we move to the Fourier domain, that just becomes 0. And so there actually won't be any effect on the register in that case. But that's okay. You can check. You can still check that you can check whether the parity transitions from 0 to non-zero just by looking at the contents of the Y register. However, for subsequent queries, you could go back and forth, right? So even if you know that you transitioned from the parity being 0 to non-zero, the adversary could make more queries on com after you measured it, and this would move the parity around to between 0 non-zero, 0 non-zero. And the problem is that once we program the random oracle, the parity can't do the check of what the parity. They can't learn what the parity is, so they can't do the check in order to prune these extra paths, which could be interfering destructively with the algorithm. Does that make sense?
I think so. Thank you.